the most important class of drugs in the treatment of HIV are the so-called protease inhibitors. Those are very, effective at the beginning, but just like for the nucleoside reverse transcriptase inhibitors and the other reverse transcriptase inhibitors, then resistance can develop rapidly. This class of drugs, we'll spend some time discussing them because they are particularly notable for the way they were developed. So they were developed by analyzing the structure of the viral protease and then coming up with compounds that could dock into that and act as inhibitors. We are also seeing several of these inhibitors previously when we discussed transition state analogs as inhibitors for drugs. So these are all these proteases belong to the aspartyl proteases. So they catalyze the cleavage of the peptide bonds and they have aspartic acid at the center. And this is actually a dimeric protein. It's highly symmetric. And we'll see that the symmetry plays out in the sequence of the protein. They recognize a particular sequence on the GAG viral protein that gets processed by the viral protease, and that's the sequence over here. And particularly, the bond between proline and F or Y, so phenylalanine or tyrosine gets broken. And here in this structure, what we see is the 2-aspartate and the molecule of water at the center of the action point. That's the substrate docked into the crystal structure of the enzyme. So if we can see, the top part, the flap part of the enzyme is involved in the action, and then the bottom part is involved in the recognition of the substrate. So let's look at the key interactions once again. So we have the flap region here and the catalytic region with the 2-aspartates. The water, that holds the substrate in place, and all the various interactions to the extended backbone of the protein that is the substrate. The reaction mechanism is pretty straightforward, just many other proteases, and so we have seen something like that. We have at the center 2 aspartates. One is protonated, the other one is not, and a water molecule. And so first we have a protonation of one of the aspartate component, attack of the hydroxyl component here to the carbonyl part of the peptide bond. At the same time, we have protonation assisted by the second aspartic acid now. We form this tetrahedral intermediate, which is symmetric, and that should, remind you of what we have seen in previous modules. And then in the end, basically, we have passage of a proton from the aspartic acid rather here to the amide, resulting in this component, and at the same time deprotonation of this second alcohol moiety and creation of the carbonyl group. So when people started to think about protease inhibitors, what they looked at was the amide, the tetrahedral intermediate that's formed during the action, and they decided to go off to a hydroxyethylamine transition state isosteron, which basically one of the OH groups was changed into a hydrogen. That is to trap the intermediate and prevent the evolution or the cleavage by the enzyme of the bond. And here once again is the sequence and the point where the cut is made. So the lead compound was starting from the natural peptide and then was altered to facilitate the ADME properties. So we have mainly, the hydroxyethylamine isoster here, And then isoleucine was replaced with this T-butyl group, which is also a protecting group. And the rest of the protein was mimicked with this benzyloxycarbonyl group, which is again a protecting group. Um, and this was, still very much peptide-like, had high molecular weight and had several authentic peptide bonds, which made it both vulnerable to proteases and also not very bioavailable. It's a weak inhibitor, however, and basically it can be trapped inside the enzyme. One important difference between protease inhibitors and other compounds that we've seen in the previous module is that we can carry out in vivo, rather in vitro tests to measure the efficacy of these compounds, because we have the enzyme, and so we can clearly monitor how well these compounds work in preventing the cleavage of a given substrate. And so that facilitates discovery. In contrast, the reverse transcriptase inhibitors were prodrugs, and so they needed to be metabolized to their active form. So from this lead compound, scientists used what we call simplification strategy, which we covered when we talked about lead development in module 3, to get to something that was a little more druggable. So the idea was to focus on the minimum prerequisites for cleavage. And so just focusing on this dipeptide, FIPRO, which remember is here, and it's basically what gets cleaved off in the reaction. All right, so from here, the idea was, again, first we insert the transition state isoster that, here in green, that we already covered. And basically that mimics the transition state during the reaction. Now remember, the transition state actually has a dialcohol, so something that looks like this, right, at the center. And we can't do that because the structure will be inherently unstable, and so will be cleaved just like it will be cleaved in the peptide bond. So from here also we included the protecting group Z and terbutyl that we have seen before, and those are useful because they reduce the overall charge, and they also provide additional hydrophobic interactions with the enzyme. And remember, we have the benzyl side chain and the proline side chain occupying the P1 and P1 prime pockets on the enzyme. So this inhibitor was weak, had basically an IC50 of about 6.5 micromolar, which is not great. And from there, scientists then utilized an extension strategy to attempt to, increase the affinity. And what they did was basically going one step at a time, inserting the group, the asparagine, that occupies the subsite S2, and that results in increased binding and a much better inhibition of the enzyme, so 40-fold improvement. From there, we then have other changes that were made to get to the final drug, and one was using this quinoline as protecting group instead of the Z group that we found before. And the quinoline is aromatic and docks well in the pocket of the P3 of the enzyme. And the next step that was going to be taken was to modify this area here. So we now, we are continuing to increase the inhibition constant. And the idea was basically to look at this whole area, also the proline and the butyl, to see if something else could be done. And that, yielded the final compound, saquinavir, where we now have a terbutylamide, and we also have this decahydroisoquinoline as a side chain. instead of the proline. We now have further increase in activity with an IC50, which is sub-nanomolar, so really good. The other improvement that we have, obviously, was with binding constant and also with bioavailability, and this is the first protease inhibitor to be used in the clinic. And then notice also that the stereochemistry for the bioisosteric group is actually necessarily, locked to be R. So let's review the binding interactions in sacubitril. Those were found by crystallography with the enzyme, and we have that 5 subsites on the enzymes occupied. And so those subsites going from S3, S2, S1, S1 prime, and S2 prime. Remember, the enzyme is a dimer, that's why we use the prime notation. These are sites that are usually occupied by the side chains of the amino acids involved in the reaction. And here we are using, different groups, and particularly for S1 prime, S2 prime, and S3 that are not amino acid. What else? From here, though, we couldn't reach the S3 prime subsite. And the other things that were noticed in this structure is that the carbonyl groups bind in the pocket, and they bind to the water of the the bridging water found in the flap region. And so in here on this part of the molecule, right? So we have this one and this one that bind to the bridging water. So with that, we have an example of a rational discovery of protease inhibitors, and we'll see in the next video what else could be done and how we derived other potential drugs.